So let's jump into the article of Robert Kraftgamer and Tal Wagner in 2016. The title is Cheeger type approximation. In spectral clustering, everything is about Cheeger type inequalities, higher Cheeger type inequalities, eigenvalues, projection into spaces, and these things are the most important things in spectral clustering. For example, the work of Spielmann or those things. And Cheeger type approximation for sparsest cut is the title of their article, sparsest ST cut. Not sparsest cut, because we have S and T as well. We want S to be S and T to be in a spar. So we want the sparsest cut, but including that S is in one of them, T is in another one. So S and T are in different clusters. So what do we do first? We should define that what is total capacity. This is if you just sum all of these capacities, it's just the total. What is the total demand? If you just sum all the demands of your vertices for any edge in E, and for any of them, it becomes the demand. And the sparsity is just sparsity of cut. S and S bar is just 1 over C capacity, 1 over C demand. So because we assume that this demand is 1, C is 1, so we just need to minimize the capacity of U and V divided by capacity demand of U and V. And the demand is very interesting because in a special case of product demands, we say that demands of U and V is just mu of U dot mu and V. And these are distributions over vertices. And a very simple example that comes to my mind is just we say that mu of V, the distribution, but at point V, at this point, is just the degree of vertices, a vertex V divided by 2 times number of edges. And as you can easily prove that this is less than 1, and we use in random walk, all of the random walk mixing and all of those things is about that. But a better example that I really enjoy is that we can define U to be average degree of its neighbors. That reminds me the work of that Iranian guy in Cambridge. I forgot his name. That he used it for semi-supervised learning. I forgot his name, but he minimized an objective, and the solution was just the harmonic function. And that's why this average degree plays an important role. So I was saying that the demand could be anything, but for the simplest say it is the product demand. We say product demand. This is the product demands. This one is product demands. And now I want to talk about the problem of ST sparsest cut. But let's say that when mu of V is proportional to degree of V, so this is just the capacity of U and V. So this is the capacitated degree of V. And the sparsity of your graph is bounded by, we want to prove that this is bounded by 8 opt. And opt, I mean the sparsity of optimal cut. And as you have seen, if you have seen my lectures on approximations, I talked about the simplest type of sparsest cut that I used for STP. You just minimize Vi minus Vj squared subject to this triangular inequality. Vi minus Vj plus Vj minus Vk squared is just the triangular inequality. We put it to make it, so we usually call it in the literature L2 representation. We say this is it satisfies the L2 representation. I have explained it in my playlist for approximation algorithm. And another constraint is just Vi minus Vj squared equal to 1. And the idea is that we want to promote something to be to find the sparsest cut. And unfortunately, the integrality gap is order of log n. This is the integrality gap. And the optimum is alpha of g n over log n. So we can improve it very much. But that is a sparsest cut. But the problem that I'm talking about is ST sparsest cut. So S and T should be in different clusters. So we say that ST separating cut with minimum sparsity. So first we should define what is a map that is ST sandwiching. We say that F is ST sandwiching if you might expect that this is sandwiched between S and T. And we can also generalize it to RP. So even this one is said to be ST sandwiching if it satisfies for each coordinate. And now a very interesting lemma that you can use in your article as well. Because if G is a, let's say G with some vertices and fixed capacities and demands be the sparsest cut. And let F from V to Rm be a map such that then we can say that there exists a cut Sn S bar such that the sparsity of G of Sn S bar is upper bounded by capacity U and V, F of U minus F of V divided by demand of U and V, F of U minus F of V norm 1. Here norm 1. And given F, this cut is efficiently computable. And furthermore, if F is ST sandwiching, then the cut is ST separating. And the proof is very simple. The proof is based on, so the proof uses just these interesting things. That first we define S tau to be, so we create our cluster like this. We say that Fi of V, all of the vertices that Fi of V is bounded by tau. So this tau is here. So we create our cluster like this. And as you know, F is just, it's a vector because F1 of V, F2 of V, and Fm of V. And the idea is that expectation with respect to tau, so any tau that you draw from just a uniform distribution, the expectation of, and this is the indicator of set, x2 of V, so this expectation is equal to F of U mathematically you can write that as f of u over f maximum minus f minimum. And because the SP, first of all, f of u minus f of v, when I say norm 1, it means that you can write it as fk of u minus fk of v. So it suffices to do it for just one coordinate. So I was saying that the sparsity of S tau and S tau bar, this is just so one thing, if expectation of that is less than something, then you can find even less than minimum of that. I mean, the proof is just using the fact that this is the capacity of u and v, x tau minus x tau of v, x tau of u minus x tau of v, over just the demands of u and v, and x tau of u minus x tau of v. And this is less than equal to this. And the proof uses this. I mean, the idea is just this. But first I should define that we say that this semi-metric D from vertices into R, of course it is positive, is ST separating if D of ST is equal to D of SV plus D of V of T. So it's like SVT. So it can be an infinite graph. So it's like S and T plays like the diameter. D of ST is like diameter of your graph, and there is a lemma that says that. Of course, this lemma, I have seen it in 1995 article, Geometry of Graphs, of that guy, Mr. London. I remember it, 1995. That proved a very interesting proof of Bourgain theorem about those metric embeddings. But anyway, so the dv of A is less than d of V and U. D and U and A. So you see, one idea is repeated in several articles because it is very natural concept. Everybody loves natural concepts. So the definition of your embedding, let's say, is that F sigma. So this is an embedding in that paper, 1995. But these papers are also using it because it's very interesting. It's just the D of your vertex and S is your source, plus sigma. Sigma could be either 1 or minus 1. D, V, and A. Oh, of course, I think Satish Rao has also used this embedding as well. So F plus A is, by definition, F plus A is half D of V and S plus D of V and A. And similarly, if we define these two functions because they just go to R, and then by using them, now we are ready to define a embedding in R2. F plus minus A is just F plus A, F minus A. And from this, we define another function called G, which has higher coordinates, and then apply that lemma. And this is the main idea of this article. So, for example, it has many, F has good properties. It has true Lipschitz property. For example, we can say that F plus minus A of V, this is true Lipschitz because this is 2 D of U of V. Also, it has another interesting property. It is a property that it is lower bounded by, for example, it is lower bounded by half d of u and a minus d of v and a. And also f plus 1 has another property, is that it is st sandwiching. So it is between that for any of its two coordinates. So what I wanted to say, which is interesting, is that let's say we define LP to be minimum of capacity of U and V. So this is just a relaxation of ST sparsest cut, because if you just solve this such that the sum of demand of U and V times d of U and V equals to 1. Of course, there are many constraints. D of V and V is 0. And it is symmetric. D U and V is D of V and U. It satisfies triangular inequality. That's why U and V should be less than U and W plus D and W and V. It also should be ST separating, so ST is equal to D of SV. So the most natural thing that you can see for, so this is just the relaxation, LP relaxation of ST sparsest cut. And I just want to prove one more theorem, and that's it for today. The theorem says that there exists a randomized polynomial algorithm, but it is randomized, that given an instance of this ST sparsest cut with vertices, with n vertices, it outputs a cut of sparsity at most O log n, opt. When opt is just the optimal sparsity of ST cut. The proof is very simple, because assume that you have solved that LP that I've just told you. So you have that LP, okay? We assume that you have solved it, and the optimum is LP. And D is that the solution to that LP, as I said. So D is ST separating semi-metric, so LP is less than opt. It's always less than opt, because it's just a minimization of that. And we just apply theorem that about something about that metric embedding that says that f plus minus u minus f plus minus v is greater than demand of u and v, d of u and ai minus d of v and ai. And now from f you can create that g that I promised you. So it has higher coordinates, and as you could expect, it is just defined by f plus a1. So all of these a1, a2 through ap are random sets that are defined in that article in Mr. London in 1995, Geometry of Graphs. He proved the theorem of Bourgain very clearly, and I've explained it in my playlist in metric embedding. You can watch that, of course. So assume that you have watched my playlist, so you can see that how these A1 through AP is created. So F minus A1 of V, and then you go until F plus, because for any set AP you have two coordinates. So 2 times p, it is 2p. It is 2p coordinates. So using this, what I want to say is that you can write the capacity of u and v, g of u minus g and v, norm 1 of that, divided by. So this is the thing that we were looking at. We wanted to minimize that because this is the ST sparsest cut problem. So this is upper bounded by